Hello, everybody. Good morning, good evening, good afternoon. And yeah, thank you for joining to part 2 of our Neo4j training series. This week, intermediate Cypher with Adam Cowley. Hi, Adam. How's it going?
Hello. I am very good. How are you?
I'm good. I'm in Cologne today. So tomorrow we have Graph Summit Cologne. So if you are anywhere on the globe, basically, Neo4j has kicked off Graph Summits. I think last week was the first one or 2 weeks ago in Dublin. This week actually. No, what's it? Yeah, this week, London, and Stockholm. So if you are anywhere in Europe, at least it's where it's starting now, and it continuing over into APOC in May, June, and then for sure also in North America. Later this year. So if you are somewhere and want to talk to actually Neo4j colleagues, hear from customers and stuff like that, so check it out. Go to neo4j.com/graph summits, and then you see all the events laid out there. But today, excuse me, today we're gonna dive in a little bit more on the other side, more technically and more hands-on. So super excited to have the second part of the workshop going. Just to make sure everybody knows how the lineup looks like. So we did last week we did intro to Neo4j with Michael. Today we're doing intermediate Cypher with Adam. Next week Will is up with building a routing application. So that's a very interesting geospatial data set and working with geospatial data. And then we have a short break and coming back on 12th of April, Spring Data Neo4j with Garrett. So the 2 upcoming trainings are still open for registration, obviously. So if you are interested in any of these other 2, then go to the website, use the QR code or the link I will post in chat now to register for the upcoming ones. So hopefully, we'll see you on one of the other ones. In the meantime, before we dive in with the intermediate Cypher training today, I'd like to say, obviously, welcome everybody. Thank you for joining across the streams. If you are watching this on Big Marker, this is obviously where you want to be in terms of, I would say, first level support. We have our dear colleagues Elaine and Will in chat as well as in the Q&A section. So if you have any questions, anything you are not sure, anything you're stumbling across that it doesn't make sense for you, or where you have any more detailed questions, then use the Q&A section. Elaine and Will have a look there. Will help you out with everything you wanna throw at them. So we will. I guess we will take a couple of questions as well, Adam, during this when time permits. So I think we should be able to cover this all. If you are wondering about slides, if you're wondering about video recording, yes, it will be recorded. Yes, we will have slides, and the slides we will share with you afterwards. So you get a link in your inbox when you registered with the email you registered with. I see a couple people. That's great. Isaac from Mexico, David from London. He was there at the Graph Summit yesterday. So you got a full on Neo4j week. It's great. You're not sick of us. So good. Hope we can bring on the continue the vibe and continue the graph fun with this training series. So yeah, I think without further ado, I'll hand it over to you, Adam. And yeah, have fun, everybody.
Excellent, cool. Well, I'd like to apologise for everyone up front who is watching this live or is even watching it back. I've got a little bit of a cough still from last week, so I may be coughing and spewing all the way through this. But hopefully what I'm going to do today is to build on Michael's session from last week. Now, if you didn't attend Michael's session last week, is no problem. There's going to be a recap. we're going to go through and look at a few things Cypher related. So firstly, I'm going to go through a recap of the what's covered in Michael's session. So the fundamentals of graph databases and Cypher. And then I've got a few slides on how Cypher queries work from a technical point of view. And then we'll go into how you can game your graph, I suppose, to take advantage of the benefits of Cypher and the way that these queries work. And then we're going to dive in and do some hands-on Cypher topics. And I want you to throw your questions at me. I want you to try and stump me, try and catch me out. So I have prepared slides up to a certain point, and then if no one comes to me with questions, then this is really going to tail off quite quickly. So let's see what we can do. Cool. If you want to follow along, I think what I would suggest is that there's quite a lot of content and slides. So what I would suggest is now if you head over to console.nefj.io and then either sign in or register, and then once you're logged in, click on this new instance button, select the empty instance, and click create there. What this does, it will give you a password, and it also allows you to download like a .m file, an environment file, which has your username and password, which I strongly suggest, because I mean, there's no way that I'm going to memorize this password. And then you can just click confirm that you've downloaded the credentials. You'll see this spinning thing. It'll take a few minutes to start up. But we'll come back to this a little bit later on. And then once that does start up, I'll remind you at the time. But you can load this data set very quickly by clicking the open button next to your database, and then you open up a tool which is called NFJ Workspace, which is a combination of low code and code tools for exploring the graph databases and Neo4j. So what you can do is if you click on the help icon in the top right-hand corner and then go to this Getting Started guide. If you skip, I mean, you can go through this in your own in your spare time. I'm not going to cover this much today. Maybe cover it in a slightly different way. But if you skip through to the fourth slide and then click this Get the Northwind Dataset button, what it will do is it will load up the data model and a set of CSV files into the import tab and a pre-built model. And then if you just hit the Run Import button, it can run off in the background. I think it takes a few seconds, 5-10 seconds to load the data in. It's not a huge data set, and then we can play around with some queries from there. So the topics I'm going to be covering today is kind of an abridged version of the content that we have inside Graph Academy. So Graph Academy is our free online self-paced training platform. There's 30-something courses there at the moment, and we're adding more almost every single day. We're improving what we have there. But the idea is that this should be able to teach you everything that you need to know to be successful with Neo4j. So we start off with the kind of topics that everyone is interested in, the beginners, the beginners courses, ranging everything everywhere from the fundamentals of Neo4j itself, all the way through the Cypher fundamentals, how to query a graph database, how to model your own graph database, and then importing data in. And then we kind of split off into curated learning paths for people interested in different things. So we have a track of Cypher courses for learning everything you need to know. The more advanced Cypher techniques and topics. For data scientists, there's a set of courses which cover everything that you need to know about the Graph Data Science Library. And if you are a developer like me, then you may appreciate one of these courses in the language of your choice. We have one course per official driver. With that being said, let's jump into, like I say, an abridged version of the graph database fundamentals and Cypher fundamental courses. Let's see where we go. So in this diagram here, we've got circles and we've got arrows connecting them. This is the structure or the structure of a graph. Graphs essentially consist of nodes, and these nodes represent things. They represent entities. So in this case, it's a MacBook. It could be a product. It could be a car. It could be a location. It's something physical. So we can identify these nodes with one or more labels. So we can assign a label to essentially group a node. And allow us to retrieve that later. There can be one or more labels. So in this example, we have a product, but it's also marked as fragile. We can assign properties to nodes in key value pairs. So in this case, we have a name property, so it's a MacBook Pro, and then we have the price, which is $2,699. We use relationships to connect these nodes together. So the lines between two circles, we call these a relationship. A single relationship will connect two nodes. They have a type. So in this case, this is a rated relationship between a customer and a product. These have a direction, although you can ignore this direction or query in either direction at query time. We can also assign properties to the relationships as well. So the context that we have here from the properties is that a customer with the name of Adam is rated a MacBook Pro with 3 stars. He must not be too happy with the quality of the product there. And the way we query this structure of nodes and relationships is with a language called Cypher. So Cypher is a declarative query language that allows you to identify patterns in your data. So in this case, a customer who is rated a product. And we do that by drawing the patterns on screen using an ASCII art style syntax. So for example, here we have the two nodes. We use rounded brackets to kind of draw this circle. And then we can use the colon to define the information that we are interested in that pattern. For the nodes, in this case, we're defining the labels here. So we have the customer on the left and the product on the right. In order to draw the relationships, we use dashes. So we specifically 2 dashes. And then we can use a greater than or less than arrow to denote the direction of that relationship. So in this case, the relationship is going from the customer to the product. We use square brackets to draw a box around the relationship. And like with the nodes, we can use the colon to specify the information about the relationship. In this case, the relationship type with a colon. And then with all of these patterns, what we can do is we can assign a variable to each one of these elements, nodes and relationships. So then we can process them. We can pull information from them in the future. Now, the way that we read from a database using Cypher is using what's called the match clause. So in this case, we have we use the match clause at the start, and then we define our pattern. So we're defining a pattern of, or we're saying to the database, find me a node with a label of customer and give that an alias or a variable of C. Then we want an outgoing rate relationship to product. And then once we have that pattern has been found in the database, we can use the return clause to return information about those nodes. So we want the customer name there. We're given an alias of customer. We want the name property of the product. In this case, we're calling it the product. And then we're taking the stars property from the rated relationship, so R, and giving that an alias of rating. So, and the way this works is when we define this pattern, and we call the match clause, what Neo4j will do is it will analyze this query, and it will work out a starting point or some anchor nodes to start this query. So in this case, depending on the shape of the graph, the database statistics, we will determine that the query will start at this customer node. And in this case, we've got a constraint on the customer ID property. So we're looking for the node. We go away, check an index to find the A node, which has a customer ID of Anton. So now this is where the benefits of the graph database come in. Once we have the start nodes and these anchor nodes, we then expand or traverse out through relationships by type and direction until we fulfill that pattern. So right now we're expanding out through all of the purchased relationships for that customer until we get to the node on the other end, and then we check the label on that node to make sure that that's and it has the node has a label of order. Then expand out through the orders relationship and outgoing direction from that order node to another node. We give that a variable P, and then we check that that's got a product label on there. Then again, expand out through the part of relationship to find a category. In this case, it's CC. And then one really nice thing that we can do with a graph database is we can specify variable length paths. So we have a hierarchy of categories here. So we have the electronics category, which has a child category of computers that has two subsequent child categories of laptops and accessories. And then what we say inside this pattern is from that CC node, that original category node, traverse out from 0 to 3 degrees until we find a category with a name property, which is electronics. And then we return everything from everything that we've given an alias in that query. Cool. So that's reading from the database. We use the match clause. If we want to write to the database, we have a few options. So we can use the create keyword to create a pattern in the graph, or we can use the merge pattern to attempt to find or create a pattern inside the graph. When we have nodes and relationships that we've found in the database, we can use the set property to either add a new label to a node or to set a property on a node or relationship. And we can use the remove keyword to remove either the label or from the node or a property from the node or relationship. And if we want to delete an element from the graph, so either a node or a relationship, we can match the pattern, and then we can use the delete keyword to delete that value. So let's take a really basic example of creating a customer. So we have this user story. As a customer, I would like to register for the website so I can buy my groceries online. So it's a really, really simple pattern here. So what we do is we use the create keyword to signify that we want to create a pattern in a relationship. Now, in this case, the pattern is a single node pattern. It's a node. We want to give it a label of customer. And then we can define properties as key value pairs using kind of like a JSON style syntax here. So we're assigning a customer ID, which is a random UUID. And then we've got the name, the address, and the country. So I also mentioned merge. So merge is different to the create in essentially it will try to find the pattern for you before attempting to create it. So if we run that create statement 5 times, it will create 5 separate nodes in the database. However, if we use merge, it's kind of like an upsert. It's a find or create. So it will first attempt to search for the pattern and find the pattern, and then if that pattern cannot be found, it will then attempt to create it. So the idea is you would use a merge statement when a nodal relationship may exist in the database, or may not, or where you want to eliminate the duplication of data. So what the merge statement will do is it will try to find the whole pattern. If it can't find that whole pattern, then it will attempt to create the entire pattern. So little tip here: it's best to break that pattern down into smaller pieces to make sure that you avoid trying to create duplicate nodes. So as an example, this is an example of a bad statement here. So this is I guess the first thing that so definitely the first thing that I did when I tried the merge statement, but the first thing that many people do is I will try to do too much in one statement. So here, if the product does exist or the category doesn't, or the category exists and the product doesn't, or even if both of those exist but the relationship between doesn't, it will try to create that relationship. It will try to create that whole pattern. So it'll try and create the new relationship and the two nodes. So if I copy and paste this, I can show you exactly what and here. So if I head over into my Neo4j workspace, if I take a look at the constraints that I have on the database, I can see that there is a uniqueness constraint on the label of category and then the property of category name. So if I search for that category with the category name of beverages, then I can see that already exists, right? So if I then search for the product, with the product name of Beavertown Nickel IPA, a little bit of a mouthful there. So I can see that doesn't exist there. So if I try now and run this this query, because this node here doesn't exist, regardless of whether this one does, it will try and create the whole pattern. This then gives me an error to tell me that a node already exists with that label and the category name of beverages. So what we should do instead is break that down into smaller pieces. So we first merge the categories that we're interested in. We then merge the product node, and then we merge the relationships between them. And then this will one by one try and find the elements, and then if not, create them, and then create the find or create the relationships between. Cool. So regardless of whether we use create or whether we use match, we can use set or remove. But in this example where we have this this merge statement, what we can do is we can set properties and we can create labels conditionally. So what this is saying is we use the merge merge statement to merge a product node with the name of Beavertown Nickel IPA. And then what we can say is on create. So when if the node is first created with this query, then we can set this property, so the created app property, to be the current date and time. If the node already exists in the database, we can set in this case an additional property there to say that it's a restock product. So we're doing maybe doing an import on like to update stock levels, we can say this is restocked. We can use just the set keyword to set a property regardless of whether we use a merge or whether this is a merge and it's been created or matched. We can set a property. So in this case, set the updated app property to be the current date time. And then we can also remove things. So in this case, where if that node does exist, then we'll remove the out of stock label from that node. Cool. So like I say, I'm probably going through this quite fast. If anyone's got any questions, please feel free to post them out. Otherwise, I will keep going through until we get to the end of these slides. But so now we've got our the concept of a database, the graph database. Let's look at how we model it to our advantage. So if you're coming at a graph database from within a greenfield project, if you're looking at it for the first time, what you would normally do is you would derive the data model from your use case. So you'd have some problem statements, or you would have a product specification, something that you can extract your data values from. And what we recommend to do really is to look at the nouns and the verbs and then the objectives that you have in your problem statement, or in this case, a user story, to drive the graph model. So we can identify the nouns that are in the database. So in this case, we have a customer. So as a customer, I would like to order laptops and accessories, and we can kind of infer from that laptops and accessories, they're products really. So these can exist as values in their own rights. So you can see on the right hand side, we now have this graph here. We have a customer node, and then we have two products, one which is a laptop, one is an accessory. We then use verbs mostly to define the relationships between properties. Between nodes. So in this case, a customer orders a product, so it makes sense to use that as a relationship type. Here I've gone for ordered as the type, because it's always something that would happen in the past. Something, as soon as somebody orders something, is ordered. So in this case, we've got the date that it was ordered as a property on that relationship. And then we can use the adjectives that are used in the user story to color the graph, really, to add structure to it and to add information. So laptop and accessories, we can use these as category names in a hierarchy. So you have the electrical category there, which has child categories of laptops and accessories, and then you just iterate on this process until you get to a workable graph model that will answer the questions that you pose of it. Now I've said that, I'm going to break that rule immediately, and I'm going to talk a little bit about intermediate nodes. So in that in that model before, we used the verb of order to create this ordered relationship between the customer and the product. Now, that might be fine for the use case. It might be enough to know that a customer has ordered a product. So, for example, if we're doing some sort of recommendation, people who bought this also bought that, it might be enough to know that. But what we can do instead is extract out that relationship or that property into a first-class citizen of its own inside our data model. So in this case, we extract out the fact that something is ordered into a node of its own, and then that allows us to link it to multiple things. So not only are we now grouping the products that exist inside that order, but we can also link it to other facts, like, for example, an order has been fulfilled by a particular shipping company. Cool. And then the age-old question that I've definitely been asked quite a lot over the years is, should I store something as a property? Should it be a node in itself? Should it be a relationship? And the typical consultant answer is that it depends. It depends on what you're going to be using it for. But let's go through a worked example here. So this is a JSON object now, which is has a duplicated address in it. So maybe this is the form data that's been posted through by a website. Maybe it's something that we're consuming from from some sort of message queue. But we have a duplicated address here, which is exactly the same as the address is the top order item in this object, but also the shipping address. Now, many databases will duplicate data for read time performance, and that's absolutely fine. It's something that we'd expect for use in Neo4j as well. But actually having that property as part of the graph may be able to enhance what you're able to do with it, and it may be able to just in general to improve how you work on the data. So I mean, like I say, like storage is cheap. So if you duplicate the data and you only read it once, or if your only purpose is to read that data back, then actually it makes sense just to keep that as a property. So this could be 5 individual properties for the address, the city, region, postal code, and country, or this could be an array of strings to represent the address. But on the other hand, if the billing address or the shipping address are saved as part of the checkout process, or something that's hinted to the user or supplied to the user when they provide their next order, actually it makes sense to store that in a node. And then we can follow a relationship from the customer node to the addresses, and then list those on the screen as the user completes their order. Now, a local delivery company that I've used in the past week, basically they give you an offer where, like, for your first order, you can take 20% off your order. Now, in the T's and C's, kind of hidden in the T's and C's, that is limited to one per address. So if that's the case, what you could do is when you're creating your user and address nodes, you could store you basically use the merge statement to merge in the customer, merge in the address, and then when you return that information back to the application, where we're working out whether the user is actually eligible for that offer, then you could return a degree count of the number of relationships going into that address, and then use that as an indicator of whether they are eligible for that offer or not. Cool. And if we're going ultra graphy, like solving real graph problems, is that graph or is that data is the address used to optimize the delivery routes? Then absolutely makes sense to store it as a node there. And then, so I mean, soon as we're working with the Northwind database, let's take a RDBMS to graph, relational database to graph approach this as well. So this is
Adam. Okay.
Yep.
There was a question on the on this last bit, and maybe we do it now. Otherwise, maybe we go a little bit too far away. Shekar says, in the example of nouns and verbs, I did not see the last statement used in graph modeling. Last statement also has nouns and verbs. Wanted to understand why it was not considered to build the graph model.
Sorry, could you repeat that?
Yeah. So I think when you talked about in the example about the statement used the nouns and the verbs and to build up the the model, he says the last statement also has nouns and verbs, but he wanted to know why it was not considered to build for the graph model.
So the so that I can in the user story, is that?
I think that's what it is. Yeah.
Yeah. I think really with that part of the user story, I guess that's the kind of bit that I've always kind of phoned in, but it's more the action is in the I would like to rather than the so that I can. So we would be storing in the Northwind database, for example, in any retail database, we're storing the information about customers and their orders. We don't necessarily worry about what they're going to do with those orders once they've got there. It's more of a this is maybe more of a trivial tongue-in-cheek example of why we would why that person would actually buy that laptop or perform that action.
Yeah. Okay. But it could be. There's no immediate reason why it could not also be part of the graph. It just you decided you didn't want to put it in there, but could be like I don't know, if we don't talk about in this case, it's more like a online retail example. If you say, okay, we want to do more like a social network or something else where we want to say, okay, have users, we have items users have, and then we also have interests. So I can say, okay, I'm a user. I have a graph database, so I can build a website with it because I'm interested in this kind of stuff. So different scenario, different use case. Then it would make sense to put it in this case. For a retail shop, it's not a point. No, the retail shop doesn't need to know what you want to do with the products you buy, and you don't want to tell the shop what you do with the products you buy.
Yeah. I guess like taking the social network example. you could do something like to take it as a introverted person. I would like to join a group or participate in a discussion so that I can connect with other users and like become friends with or build friendships with other users. There's no reason why you couldn't use the so that I can in that example to inform that will be what you would call the relationship that gets created between the two users once they've interacted and become friends.
Yeah.
So cool. Hopefully that answers the question. If not, then feel free to ask a follow-up. Okay, so let's look at relational databases to graphs. So for anybody that's not familiar with this example, I'm probably dating myself by saying that I remember this. So I remember learning this in the early 2000s as an example way of like working with a Microsoft Access database, and really it's become one of those de facto examples that you that you would use as a way to explain and to teach relational databases. But really what we want to do is we want to turn it into something like this. We want it to turn it into a structure of nodes and relationships. Now, there are easy ways and hard ways to do this. To look at the easy way, we could essentially just take the tables, or the majority of the table names, and then convert those into labels. So we'd have like a label for a product, so we could search for every product in the database, or every customer, every order. And then the rows in those individual tables, they become the nodes in your database, which are identified by those labels. So you are searching by a grouping. You're just doing it in a different way. It's just a different, I guess, a little bit of a paradigm shift. So in a relational database, you have this concept of a foreign key. So usually a number, but a reference in a table to a record in another table. Now, in this database, there's a lot of straightforward foreign keys in there. So, for example, a product will be part of a category. A supplier will supply many products. So we have like in a products table, we have a supplier ID, which then is a reference to the supplier ID primary key in the suppliers table, to kind of hold that one-to-many relationship. So one product will hold, one product could be supplied by many suppliers. No, sorry, it's the other way around. So each product will have one supplier, and a supplier will supply many products. So a lot of these, the natural way to model these will be just to turn these into relationships. So rather than having this concept of a supplier ID in the products table, we can actually link that directly, and we're almost drawing an arrow between the two items. So we are saying that a supplier supplies a product. And to me, this is a more natural way of modeling data. And I say this because of the next example that I'm going to go on to. So we have this concept of a link table as well in a relational database, where a table is created that exists to manage a many-to-many relationship between two tables. So in this case, a product may appear in many orders, and an order may have many products. So we have this table in between, and often these linked tables are only consist of foreign keys. But in this case, it kind of makes sense. We have this order details table, which has the order ID, which is the reference to the order itself, and then the product ID, which is a reference to the product table, which then allows this many-to-many relationship to be facilitated in the graph. In this case, we've got the unit price, the quantity, and the discount as well on that. And this example kind of makes sense. This one really doesn't. So we have a customer demographics table, which has a description there, and then we have a customers table, which holds the information about the customer, and then a customer. And then, so this is one of my experiences, and like naming things is in development is hard, right? So you kind of end up getting these tables, which are kind of like a mashup of the two. I mean, order details make sense, but customer ID, customer demo doesn't make any sense to me. Whereas in a graph database, we can just kind of link these two concepts together, and there's no need to create that link table that's in between. So if we take the example of an order and a product, an order can contain many products. So what we can do is just create the relationship with a type of contains from the order to the product. And then those additional details, so the unit price, the quantity, and the discount can all be applied to, or can be stored as properties against that relationship itself. Cool. And let's take a look at an example SQL to Cypher query. The similarities and the differences between the two. So this is one that I've just taken off of just searched for, I think, Northwind SQL, and came up with this one, which I think is I think it creates a view. So it's basically getting information from from an order. So we have the customer there, we have the products, orders, order details, and then the employee that sold the order, and then the shipper that actually shipped the order. So the select clause is very similar to the return clause. I mean, as you can see, that these two it's almost a copy and paste. There's just a few little changes there to make it work in Neo4j. But the difference is we define this last. So one of the things that I always found myself doing when I was writing SQL queries is that I would do I type select star, and I do from, and then I do my tables and my joins, and then that gave me the autocomplete, or like the IntelliSense, to be able to get the auto completion on the fields itself. Whereas we in a Cypher query, we define that last. So we already have the information. We define the pattern. We define what we're interested in, and then we choose the return after that. So the from statement is the second bit in an SQL query, and so here it's quite wordy. I mean, for a non-technical person, I've showed this to family members and things that aren't technical, and that this doesn't quite make sense to them straight away. It takes a little bit of explaining. What we do in a Cypher query is we define the patterns up front. And we do that by, like I say, by drawing the patterns in the data. So even though it's not completely clear, it's easier to reason about. We've got this customer. It has some sort of connection to an order. The order has products in there and ship, and there's a shipper there as well. The where clause, very identical. So I have written this with the inline where syntax. So I'm defining in that pattern itself. I've got the curly braces to denote properties, and then the customer ID property there is Anton. But actually, if I extract that out into where clause on its own, exactly the same. There's no difference there. So I mean, it's completely up to you which one of these you prefer. I know which one I prefer. I mean, I still like writing SQL, but I would much rather be writing Cypher queries all day. Cool. So we have this. Maybe we take this approach where we
Adam.
Yep.
On modeling, I think there was an interesting. I mean, we talked a little bit about this, and you said it's a very much it depends kind of question, and I agree. It very much depends on all of the all of the variables and all of the parts of your specific use case where you use graphs. How does the data model look like? But Hani has an interesting question. Is there a rule or direction of what should not be a node or a relationship? I think that's interesting. So, some of these we can obviously also say it depends, but maybe some of these we can make a little bit of a guidance.
Yeah, I guess it does depend. A lot of it depends on things like sort of data deduplication when you need to query through things. I think one of the examples that we've got is the if I can go all the way back. So we have like I guess the address is the best example, right? So you're like I say, you can there may be instances where you need that to be a node in its own right, in which case you promote it to be to be a node in its own right, and then you can use it as part of the graph as part of your queries. You can query through it. One of the big things for like for fraud detection is you would I don't know, maybe if you had like credit cards in your database, you'd store the credit card number or something, or phone numbers, email addresses, that kind of thing. And then if you see many users that are using the same credit cards or the same addresses, details, but have different accounts, that could be a sign that there's something wrong there. So you could be querying it. Where things would not exist in the graph at all is quite an interesting one. So a lot of people will use a graph database not as their kind of main source of truth, but they will use it as a supplementary database. And it may be that you have an aggregation of the data inside there, and you only solve the graphy problems in the graph database. So it may make perfect sense for you to have an e-commerce database which is entirely in a relational database, and then you just want to do the recommendation queries through the graph. Because that it's the way that it's designed. So what you could say is, out of all of this data that we've got on screen now, you may only want to import in the customers and the products and create a relationship between the customer and the products, and then you could have an aggregated view of that data. So you'd say that I don't know, the customer Anton has spent 10,000 on beverages. Or on, I think chai is like one of the example products in there, and they've spent 400 on Converse, and then you could go through and use those patterns to work out the other users with similar patterns, similar behaviors, and then provide the recommendations using that. So it's not necessarily that you have to have Neo4j as your one database. It may be that it exists on the side, and it may be that it only has an aggregated or a different view of the data in that database.
Yeah, but that does not mean you cannot use it as source of truth. You can totally do that. But again, it depends.
Yeah, exactly. Yeah, and in some cases, it does make sense to use Neo4j as a single source of truth over another database, because you can import data in, and I'll go through it's actually quite a nice segue into my next section. But you've got like this flexible it's kind of schema optional database where you can throw lots of data in, and we talk a lot about data existing in silos and connecting it up in a single place. So you could have all these different databases all feed into Neo4j, which is a single source of truth. But then you may start off with like a large bank may have legacy systems where it's not possible just to lift that out and put Neo4j in, so they would use it for graphy things. So I am paid to say that we can use Neo4j as a single source of truth, right? But it's definitely possible. It's definitely something that we can do.
Yep. Thank you.
Cool. So refactoring is a hot topic. So you've got this really nice functioning database. You've got maybe a couple of thousand customers in your database, and everything is working fine. And then all of a sudden, like you find out that your database is going slowly, or there are things that you can improve. So in a relational database, you'll go through what's called like a migration. So you will define at different points, different versions, different stages of the database. They have certain things. You write scripts to alter columns and create tables and do all these things, and it can be an absolute nightmare. Luckily, it's a lot easier to do these kind of refactorings to develop on top and to add flexibility to your graph database by refactoring it. So why would you refactor? Well, like I say, like you could have a database that isn't performing as well as it once did, and you need to do something in order to improve that. You may have a non-complete graph that maybe answers a few of your questions. You've and you work in an agile environment. You've ticked off a few tickets, but it's difficult difficult or impossible to answer the question you've got. So your boss may come to you one day and say, "Oh, you know, I need to find out some like weird edge case. You know, I need to know all of the orders from the Northern Territory where the price is more than 30 something. You know, I need to put this all into a dashboard, and it needs to, like, I need to run these queries every 5 minutes. You may need to add the concept of an address or something like that. Or your database might just not be as performant as it was when you had 100 customers in there. So there's a few methods that we can take. So firstly, creating an index or a constraint on your database is a good start of a good way of speeding up the discovery of anchor nodes. So you can create a constraint on or an index on a label and property pair, and then use that to search and to hone in on a set of nodes and then go from there. You can add a new label to the database. So for example, if a user, if somebody in the company is only interested in those fragile projects for whatever reason, I don't know why, then you can add that. You can add a new label there. You can extract out a property into a node or a relationship, or you can use specific relationship types. So I'll go over a few of those options. So I think adding a label is one of the more simple things that we can do. So let's take this example. So as a sales rep, I would like to recommend alternatives to discontinued stocks to ensure that customers have a viable alternative to their favorite products. So if we take a look in the database, and we take a look at the some of the products in there. So you can see there's this discontinued flag there at the moment. So this is an unindexed property on the node. As we find a few that are true. So so this one here is true. So what we want to do is we want to find an alternative for each of those users. So what we can say is for each of those, for each of the customers who have purchased an order in which it orders a product, where p.discontinued is true, let's just return a few of these. So we've got this Chef Anton's gumbo mix, which has been purchased by all of these people. So what we want to do is we want to provide an alternative for them. So if I actually look at this this query and I do a profile, I can see what the database is actually doing. So if you recall earlier, I was talking about the way that we find anchor nodes and then we expand from there. So what this actually, interestingly, what this has done is, even though we've written the pattern going from the customer to the product, what Neo4j has decided is that the best place to start in that traversal is to start on the product itself. And then what this does is it will do a filter down on the discontinued property to make sure that is true, and then expand through the orders and the purchased, and then go from there. So if I take a look at the steps here, we can see as we go through the graph and as we expand, the number of database hits will grow. We can also see the amount of memory that's used there as well. So if you ever do see the node by label scan followed by a filter, that is a good sign that you either need an index there, or you need some sort of label there to speed up that discovery. Because this continued is a Boolean, it's true or false. It's a good candidate to be promoted into a label of its own. So what I can do is I can find all of the products where the discontinued property is true. And again, so this is exactly the same as saying where p.discontinued is true. It's just, maybe this is just a little bit more of a succinct way to do it. So if I just return a count of that for now, we can see how many we're dealing with. Cool. Okay, so there are only eight in the database there. So what I can say is, for all of these, set p and then give it a discontinued label. And if I run that, it's telling me that there are 8 there that are 8 labels that have been added. So that's our 8 discontinued. Now, because there's only 8, this is fine. There's no need to worry about this. But as you get to larger data sets, this is a common gotcha, really, is that Neo4j is an ACID compliant database. Everything is run inside transactions. So it will try and complete the whole unit of work before it commits that transaction. So what we can do is, if we did have, say, for example, thousands of products there that aren't that are discontinued, we could run it in a or we can batch those updates, and then we can say, for example, we can call it a subquery, and then we can say that we run it in a transaction, or in transactions of, let's say, 1,000 rows. It's a good place to start. Could, depending on your memory setup, you could do more. But what we could do in there is we could say, so with p, so we're passing the reference of p into the subquery. So pass through p in batches of 1,000, run this operation, and then pass that out to the to the parent statement. 1,000 rows, and we've got exactly the same thing there, but it's batching it, so it means that we're not going to run out of memory at any point by trying to write too much to the database. And now I can rewrite that the query from before, and I can say so instead of going for the product, find me all of the discontinued products. We look in the plan, and then in the table view. Actually, what we're doing here is we're doing the node by label scan still, but we're not performing that extra step of the filter. So kind of hard to see here, but the number of database hits will be reduced, and that's one way to refactor the graph. So the speed of a Cypher query is proportional to the size of the graph that you touch, not the size of the graph in total. So by reducing the number of these product nodes that we search through, we can speed up our queries and make sure that our queries are still performant. Cool. So we can also extract out a property into a node to maybe answer a new use case or a new user story. So let's say, for example, as the operations manager, I want to find customers that live at the same address so I can reduce the driver workloads and improve delivery times by optimizing the delivery routes. Sounds like a good thing to do. So what we can do to do this refactoring is first we need to find some sort of unique identifier, some key that we can identify an address is unique, and then we can create a constraint on that property and the address label to make sure that our address only exists once. We then use a match statement to build up a list of all of the addresses and the customers that use that. Use that data to run a merge statement to either find or create an address node, and then create that has address relationship between the customer and the address. As they say on British TV quite often, here's one I made earlier. So what I'm going to do is I'm going to create an index based on a normalized version of the address details, and I'm going to call that address ID. So what I want to do is create a constraint for any node with a label of address. Then I want to require that the address ID property of that node is unique. Apparently one already exists, which is great. So you can do like create or replace, and then that will. Oh no, sorry. So create constraint if not exists. Alex, edit that bit out. Yeah, so we can create that that constraint if it doesn't exist for that value. So then, if we take a look at a customer and what the address field looks like, we have the address property there. We have the city, so this is Berkeley Gardens in London. We have a postal code, and then a region and a country. So what we could do is convert that into a normalized string. And let's say we'll get 10 of them. So n.address, n.city, n.postal code, and then n.country. So that gives us an array. And then we just kind of want to join that, remove spaces and things like that. So what we can do is we can use the APOC text.join function to join everything together, and then we'll just join it with a space. So that's no longer an array of strings, it's now just a single string. And then we can use apoc.text.clean to remove any of the spaces, convert it all to lowercase. And then we could probably change that to be a dash. So it's probably a better way to do this, but this will do for now. So I can say that with that value, I can merge the address with a address ID property of this value here. then I want to set some additional properties. So because this will be the same every time, I can just say on create set, and then it will just set that the first time. And then I could do like a I know a dot address equals n dot address, and I could just do that for all of the different properties. But I'm lazy, so I'm going to do a math assignment. So a plus equals, and I'm going to use what's called a map projection to get properties from that node. So I can say from the n node inside a map, give me the address, the city, the postal code, and the country. And then what this does is it will, so everything inside these braces with just a dot is a shorthand for n dot something. So it'd be the equivalent of that. And then the math assignment says that, so for everything in this map, assign that to the property. Then I want to merge the relationship between the customer node. I'll call that has address. And then it's return star limit 10. Yeah, so we have these nodes here that are now linked to an address. And the good thing is we can run this as many times as we want to now. The same, because this is a merge, and we're doing a merging on just an address ID, and then we're breaking things up into patterns. We will only get one. Yeah, so we've got no changes there, no records to return. So we don't get any duplication of the data in there. We can do the same thing for the orders as well. So we can say n for the order. If we just take a look at the order properties, so they're all prefixed with ship. And here's one I wrote earlier. So for each one of those customers that's purchased an order, merge this address on that ID, and then set a plus equals to those values. And then we create the has address, and then we create the shipping address. Cool. And let's create that again. So now if I look to one of these orders at random, I can now see that the shipping address is here, and that shipping address is used for quite a lot of orders there. But it's this one user which is common to those two addresses, which is now there. So we can now use that as a graph element in its own right. Cool. And then the next thing, I won't go into too much detail on this one, but specific relationship types. So let's say we've got this small graph here. We've got customers, or a customer that's purchased. Yeah.
So sorry, can we quickly go back just to explain one more time when you added that discontinued label, we did not create a second set of nodes, but we added a second label onto an existing node. So we have two labels on the same node, but that shows it that these two are, you can query the two labels at the same time, but they still have, you didn't duplicate your graph, you just added additional information to an existing node.
Yeah, that's correct. Yeah. Yeah, so you can add multiple nodes to multiple labels to a node, which allows you to either slim down what you're looking for, or provide extra context. So like booleans are a good example of something that could be stored as a label rather than a property. Then that gives you the benefit of being able to look them up quickly, and then so say for example, if we've got this. Let's take 10 products. Then we'll just take random ones. So you could say like, P dot. So just take the product name, whether it's discontinued as the property, or you could say P. Discontinued, so that you can kind of look in two ways. But actually, if you just wanted to find all of the discontinued ones, then you can go directly to those instead. And yeah, you can add as many of these as you need to. So one of the examples that I like from the days going into banks was you can have an account, and it could be interesting to know all of the accounts that a customer has. But you may also want to know all of the current accounts, or the checking accounts, or the credit card accounts. So you could use these labels to kind of differentiate between the two, and then you could use that as part of your query.
Yeah. And there was a kind of follow-up question to that, and I think it is an interesting point from Amol. Could you have just created an index on the property as an alternative? I guess yes, but the beauty of the additional nodes is just what you just said, is it makes it easier part of your queries, and you don't have to go via the property every time, but you can use the label and integrate it in your query. So imagine you have other queries where you touch it all the time. You don't have to. You can go via the index, but you also can use it like this, and this makes it a little bit more intuitive to work with, I think. Yeah,
definitely. Yeah, it's adding it as an element in your graph rather than having a property and indexing it. But yeah, I found out today that actually the performance between setting an index on discontinued and having the label, there's no real discernible difference between the two. I mean, obviously I'm working on 8 nodes here, but yeah, I think whichever one makes sense. I think one of the benefits you have as well when you're using a label over an index is that you're not got this huge index that you're building and adding more things into. Yeah, I think with something that's a Boolean yes or no, I don't think that the performance is going to be much different either way. But it makes sense to have it as an element in the graph, and then you save your indexes for things like longer strings, numbers. So you can do range lookups, contains, starts with, ends with, that sort of thing, and that's where the power of the index actually comes in.
Yeah. Like we said, you can use it for more than if you add it as a label, you can use it for all kinds of different scenarios. So I think it's a bit more versatile. But it's up to you how you prefer to work with it. One more before we go back into it. Yes, it does. Will you be sharing your Cypher queries? Will they be in the slides? Can you add them there, or is there some way of adding a page of your queries somewhere into the documentation we share with the people?
Yeah, hopefully. I'll try, and as long as I can get them all out of history, then I can share them, or a version of them. I can add them into the slides, or just create a gist or something like that. We can link to that in the recording notes.
Okay, sounds good. Thank you.
Cool. Okay. So I guess I've kind of touched on the specific relationship types when I was talking about the account types. But yeah, I mean, let's say, for example, keeping it in the Northwind database. So we've got this small graph here of this customer Anton and his purchases. So he's got 2 purchases there that are beverages or products that are categorized as a beverage. 2 items of clothing, and then he's bought 3 from the electronics category. So maybe the head of electronic sales comes along, says, I'd like to find all the customers that purchase electricals, so I can meet my sales target by recommending them some sort of upsell. I don't know. So what you can do with a specific relationship type is you can encode some information about either the node at the other end of the relationship or the path that it takes into the relationship type itself. And then in this case, we've used the category on the other end, added that as part of the relationship type. So it's probably a little bit difficult to see, but we've got purchased electronics relationships, purchased clothing, and purchased beverages. So now when we query through, we can, when we're expanding the relationships, we can ignore the relationships that we're not interested in. So over half of this customer's purchases, we can ignore those straight away. And as we expand through the graph and as we query more and more things, we'll get more performance. So there's a trade-off there of the benefits of following these specific relationship types versus the maintenance cost of keeping those things there. And it's just a trade-off, really. But for me, if you're writing once and reading many times, it makes sense to take the hit when you're writing data to the database, so you can get the better performance when you read data back from it. And cool. So we've got 25 minutes left. Let's have some fun with Cypher in it. Let's look at some more advanced techniques and some changes. Alex, is anybody had any questions for me, or has anyone come up with any questions they want asked of the data?
I didn't see any. I mean, besides the one I read out in the few, the many actually that Will and Elaine answered, I don't see anything in particular. Maybe one that came in, I just saw from Eshwar is, if you have, and it's maybe a more, I don't know if you want to go into this, but we can outline it, I think, a little bit, is how to add data to your graph. I think this is the old, not necessarily import data question, but how can you, if you have something, refactoring maybe is probably a good point. You have some data in your graph, you want to add to it. What are your options? How could you possibly do that? And what's a good pathway of connecting?
So it depends on the format that the data is in, but we have many ways that we can import data in. So if you've got a CSV file, probably the easiest way to do it is to use this import tab, and you can start to kind of draw out your nodes and relationships, your graph model, and then assign that to CSV files. And it's a really nice kind of visual low-code way of doing it. So if I run this, what it will do in the background is it will write Cypher statements for each of the things that you need to do. So you can kind of see that for the territories, it's creating this constraint, and then it's running this data. We also have the load CSV command, so you can take a CSV file from either your local computer or from the internet, and then load it in through there. So you basically assign every row from a CSV file to a Cypher variable, and then you can use the Cypher to write the data from there. We've also got in APOC some procedures for importing different types of data. So if I call apoc.help, import. This should give us a list of the different things that we support. So the two enabled on Aura are CSV and GraphML. You could also use things like import.load.json to load JSON in, or you could create use ETL tools that can connect to Neo4j either over Bolt or via JDBC. Or you could even just write an application in your favorite programming language, Python, Node, whatever, to load the data in. Then you essentially you do what the data importer does. You batch up your imports into rows of so many, and then you unwind and import those in. But yeah, I'm happy to answer a more target or give a more targeted answer if there is one.
I think that's a good point. I mean, there was one of James, how to add additional properties to existing nodes. What's the best practice for that? Could you maybe think about this?
Yeah, sure. Yeah. So I don't know if there'd be. Let's see if there's a CSV file that we can take from somewhere just to look. And I think we have all of this, but let's say we've got two separate databases that have a common identifying field, but they have different data in them. So we have I don't know, the credit card number or customer ID or something like that. Something that we can relate between the two. The best thing to do really is to use the merge command. So let's say we've got the order ID here, we've got the customer ID, and then we want to take the required date, let's say, for example. So you could download this and you could map it in the data importer, but I like writing code, so let's write a bit of code. So you say load CSV with headers from this file, and give that an alias of row, and let's just say return row limit 10. So we've got like the headers are now assigned to this row object. So we've got where's the required date? Is there? So you can see how old this database is, by the way. It's 1996. This order was created. But let's say let's merge the order where the order ID is row.order ID. And then we could say, like, for example, set o.required date to be, that's a date. A date from row.required date. I set it to be string. Let's not be too yeah. So that's say 830. How many do we have in there? Okay, so we have 830 in total, but oh no, yes, it would do because I used the merge. But yeah, if you can either merge or you could just do like a match, and then it'll only find the ones that are in that file, and then use the set commands to set properties on that.
Yep.
And then you can kind of incrementally do that. Like you can do like an incremental load to say this was Northwind orders from 1997 rather than 1996. You could run keep running the import with the different values, use the merge keyword, and then you're merging the data into the graph with and then kind of appending on top. So you would either find or create the order by the order ID and then set some properties against that one.
Yeah, makes sense. There was another one from Jack, which is probably more complicated one. I don't know if you have time for this, but you tell me. Deep dive into shortest paths, APOC path expand config versus all shortest paths when to use which rules of thumb. I don't know if this gets a little bit too far out into away from intermediate Cypher, but maybe briefly.
Yeah. So I guess we could do like a 2-hour session on that alone, to be fair. So yeah, and I don't think this data set's got any good data in it that I could demo it with. But the variable length paths that you can do inside Cypher are kind of that they've gotten better because you can define now with like IfJ5 you can define more complex paths. But with the expanders and APOC, what you can do is you can set specific expands. So you could say follow this in this direction, or follow this in outgoing direction, do something in the incoming direction. Stop at this node, exclude at this point, and all that sort of stuff. So you can set more complex rules, whereas you could just say, like I don't know, if you want to find the route between A and B, whatever they are, up to 100 degrees away, then and that was all you needed to do. So it's like, I don't know, one relationship type, or maybe 2 relationship types. You could do that, or you could leave off the direction in general. But if you wanted to do something more complex than that, then you'd use the APOC expanders or the pathfinders in GDS.
Yeah.
Cool. But yeah, it's definitely a level above what we've got.
Totally. Yeah. No, don't worry. Another one about timestamp information or date time, how to work with date time in Neo4j.
So we have temporal types. I think I wrote a blog post in this in 2016, I think, or 18. I don't know.
Yeah,
it's been a while.
Yeah.
So yeah, we have date time, local time, date time, local date time, and the duration. So the duration is just a number, but these are our kind of temporal types. The benefit is these can be indexed, so you can search for things that happen between 2 dates. Actually, that might be a good thing to look at. So let's take a look at an order. So we've got there's a required date that I've just added in there. So the order date and the ship date there. So there's 2 ways that you can create so these are all dates, but essentially it's the same for dates and times. You can create it in 2 ways. So you can either say pass an object through, so you can say the year is 2023, the month is 3, and then the day is 22, and then that will give you a date object. So you can say date time, and then it sets it to 000, and you can say hour 17, and then that gives you the value. Or you can supply a string. So it's an ISO type. I can't remember exactly what. Oh, so it's ISO 8601. So it's not exactly the same as we have in that in the file. But what we could do is so o.order date, and then we could say dates time o.order date, and it's very close. All we need to do is replace the space with a T in this case. Then that gives us our value. So assuming this is in Z, so this is in UTC, That's all we would need to do there. So we could just say like call in transactions of 100 rows. So for every 100 rows, commit the change. Cool. And then if we look at this order again. Oh no, sorry, that's the CSV file. If we look at an order again, we can now see that it is order date is now, so it's not got the quotes around it, so it's not treated as a string. It's now in our format. So we've got the required date there. We've got the ship date. Ship date. Shipped. Oh. Oh, don't. So that's giving me an error saying that, so it can't convert null into a and I think that's a string. Yeah, okay. So some of those orders haven't been shipped. So now we've got the ship date and the order date. So what we could do is with the order. So where the O dot so the ship date minus the order date is greater than or equal to a duration of 2 days. Oh, sorry. Duration. So you can extract a duration from a date, but you can't subtract a date from another date. And you can't do it on a string either. Where is not null? No. What have I done wrong there, Alex? Return. Looks fine. This no.
Should be.
Minus. Okay, so it's. I don't know if they just answer. This is definitely live. There's no polishing to this, Alex.
Yeah, that's okay. The dates are flagged as daytime, so that should be correct.
All right, so you can add to a duration. So let's. There we go. Right. So so let's say that we aim to deliver everything within 2 days. So that's a period of, let's say, 2 days, 3 hours, 4 minutes.
Yep.
So a little bit of pre-processing. So we've got the order. We have the expected delivery time, where O dot shipped date is more than equal to the expected. There we go. Cool. So I guess this is 1996. So they probably didn't have Amazon next day delivery back then.
No, maybe not.
Let's give a count. So 733 there. So out of the 803, I think it was, 733 were delivered outside of that time. So say 12 days. So only 109 were over kind of 12 days.
Mm-hmm. Okay.
So hopefully that answers the question. A little bit of a tangent.
No, I think it's okay. It's just the segment. I think you called it rightly, fun with Cypher. So we explore a little bit. We try. Obviously, you code live, and it's always a little bit of a challenge. So, but you see, there is lots of possibilities if you have temporal data. If you work with that, if that is something you need to calculate, time distances or other things with that, work with date, work with hours, work with time in general, then you can totally do that, and this is integrated, and you have lots of options to work with date time values in your graph.
Yep. Yeah, definitely. Cool. So I had one thing which I think will show off most of my favorite features of Cypher. But let's look at the so we have a sales manager that wants to find all of the customers with the highest spend, so we can reward them with a personalized offer. So we're going to do we can use the with clause, which allows us to do kind of pre-processing We'll look at aggregation functions. We'll do some map projections and some fun stuff like that. So we are looking for, if I can remember my own task, customers with the highest spend, and then we want to recommend them a product. Cool. So in order to find the customers with the highest spend, so we need to go from the customer through to the order, then to the product. The relationship of the from the order to the product has information on the quantity, the unit price, and the discounts. We'll take a look at that, and then we'll take a sum from there. So if we're looking for I'd say loyal customers in general, there's kind of two ways we can do it. We can either do it by the number of orders that they placed, or the maximum number of the order they placed, depending on the kind of KPIs and metrics as to where they would, which would be the preferred option. So if we just say, for example, would find some customers, what we could do to define loyalty is to use the number of orders that they placed. So we could say orders purchase an order. And we could actually use that degree count in order to find who is the most prolific, the people that place the most orders. So what we could do is just return, let's say, the customer ID, and then order it by a count of the outgoing purchase relationships. Let's get the top 10. Okay, so that's duplicating because it's got, yeah, cool. So the biggest one there we've got is Savior. What we can do is we can actually put that value into the return. So we call that as total orders, and then order by that value. And if we look at the actual profile there, we're not expanding any relationships at this point. What we're doing is we're using get degree. So the statistics of every node, or as part of the statistics of every node, there is a degree count of every incoming and outgoing relationship to and from it. So this is accessing a single value rather than actually having to expand anything. So that's quite a nice little touch there. But if we're defining loyalty as the total amount spent, then we'll have to go through the through the orders. So this customer has purchased an order. So what one of the mistakes that I see people do quite often is they will define the labels for everything that they're doing. So for example, we've got this pattern here of a customer who's purchased an order. So the O there is the order node, and then we've got the product there. So what will happen is say we start at the customer side, we expand through the purchase relationship, and then we go to this O node. Now, because of the way that we defined our schema, we know that node is going to be an order node, so we can just remove that off, completely. But then by keeping the labels at the start and end, it actually gives Neo4j the ability to be able to choose which ends to start with. So, and then we have the, let's call that OD for the order details. So the nice thing about aggregation in Cypher compared to things like SQL is that you have no having clause. There's no there's no kind of group by. It's all implicit. So as you use the with statement or you use a return, and you do an aggregation, it will work out based on the aggregation columns, things you've defined as aggregations. Everything that isn't an aggregation function will be used as a grouping. So let's say, for example, we'll return the customer ID, the order ID, and then we want a sum of the OD dot unit price times quantity. That's the one we're looking for. OD dot quantity. And then we want to times that by 1.0 minus OD dot discount. So I'll take the discount value off. Let me give that a total. Just take the first 10 that we get there. So this this customer has placed this order here 10692, and the value of that is 878. So as you can see, this is grouped by the customer ID and also grouped by the order ID. If I remove that O.order ID out, then I just get the total aggregated for that customer ID. So it's only aggregating on the customer ID now. And if I order that by the total in descending order, the most loyal customer here is the customer ID Quick, who has spent 117,477. So what we can do with that is we can, so for example, use this to get the first 10, and we can use, rather than using return to return the results straight away, we can use with as a pre-processing step. So to give me the most loyal customer, we can then in a subquery call with C match C purchased order for product, and then we can say return p dot product ID as product, and then we can say take a count of that to see what their most purchased product is. I guess we could also do like a sum of OD.quantity. To see how many of those they bought. And then we'll return star. Cool. So so our customer is going to be our Quick. So this is the entire customer record. Product number 60 let's return the name instead so we can see what they've actually bought. Camembert Perrier, they've had 4 purchases, 4 separate transactional purchases. In a total, they've bought 243 units, and that's the value they've spent on that. They've also bought Hokkien fried mee. In 4 purchases, they've had 191 in total. And yeah, so we've got within there, we've got the a query, we've got some aggregations, we've got a subquery there. One thing I will do before we end, so we're a couple of minutes off the end, is I will show you quickly a pattern projection and a map. So what we could say is, so we've got the whole customer node being returned. We can use a map projection here again to say, give me the customer ID and the first name, last name, the company name as the company. We want a collection of the product. So they're top products. And we want the total spent. And then let's just say, for argument's sake, we want to get all of their addresses. So C from the customer node. Has address. Always remember your commas. And there we go. So we've got a projection there to give you the information about the customer, properties against the customer. We've got a collection there to show what are all their top products. And this one, just to throw in at the end, is a pattern comprehension. So what we're saying is, for a list of all of these patterns, so the outgoing address relationships to and node, which we're given A, we're taking the address ID to then give the addresses there. And cool. With that, I think it is time. If anyone has any comments or questions, feel free to reach out to me, or yeah, drop them in the comments, I suppose, in wherever you're watching. Yeah, I'm happy to clarify.
Cool. Yeah. Thank you very much, Adam. If people want to reach you, LinkedIn, Twitter is where to go. I would say, if you want to continue the path Adam outlined today, the best place to take this on is the Graph Academy. I'll post a link in the chat right now. So go there. Like we said in the beginning, this was sort of like a medley of Cypher data modeling, a little bit of importing CSV data, a little bit of advanced Cypher, a couple of these training modules you see here on the website. If you want to learn more, if you want to continue the path, look at these, do them all, and continue your journey there. If you have any questions, the community is always open. So if you go to community.neo4j.com or to our Discord server, which is discord.gg/neo4j, then you have an open, friendly group of graphy people who will be able to help you out if you have any questions, any worries, any things you want to discuss. Obviously, next week again is another way of learning. So will be there. We talked about temporal distances a little bit. We will talk about actual distances, kilometers and meters and other things next week with map data, geospatial data. We'll do this same place, same time on the Wednesday, 29th of March. So if you have not registered for this one, please do so. Yeah, other than that, totally appreciate all of you spending the time with us tonight, this afternoon, for learning and for exploring a little bit more on Cypher and going into deeper Cypher queries. So I hope it was helpful. I hope it was useful for you. I hope you will continue working with Neo4j. I think that helps a lot, especially in the beginning. Just spin up a Aura instance and play around with some of the either provided datasets or with some of your own CSV files. Fail a couple of times with query errors, but iterate over them, and then in the end, you will learn a lot through this. Yeah. Any final words, Adam?
No, I don't think so. Yeah, like you say, it's always fun to play around with these things. The one thing that I probably should iterate on again is that if you head to Workspace, once you've got your database running, click on Open, and then on the question mark tab there, getting started with Neo4j, head there, and then you can load the data set and you can explore the data set. You can be guided through the data set, and then sign up for Will and Garrett's sessions as well to make sure you learn everything.
Absolutely, exactly. Perfect. Well then, we finish tonight. Thank you very much for watching. Thank you for your questions. Thank you for taking part of this. Obviously, thank you very much to Will and Elaine for helping out with Q&A. And thank you, Adam, for presenting and for doing some live coding on the hot tin.
It was a pleasure.
Yeah. All right. With that, thank you, everybody, and I wish you a great rest of your days. Bye.
Cheers all.